Hello and welcome again to Chem in 3. In today's episode, we connect to another video. And first, I would like you to click on the link to the card above to go to this video so that you can understand about the Gibbs free energy, about examples of spontaneous reactions, and what are the criteria for spontaneity, and to also get introduced to this equation which states that the Gibbs free energy, or the free energy, the energy that's released when a reaction happens, this useful energy that's capable of doing work, the Gibbs free energy. Once you look at that video, you would realize that a reaction is spontaneous or non-spontaneous at a given temperature like 25 degrees Celsius if it is exothermic, and if it takes place with an increase in entropy, like the explosive reaction of sodium and water, which is both exothermic, releasing a large amount of heat, and taking place with an increase in entropy as the solid sodium becomes sodium hydroxide. Both of these criteria are filled. But a system, a reaction, can have the ability to do work, and it can have a release of free energy. And if it has a release of free energy, then the value for delta G, the change in this free energy in relation to the system, becomes negative. So this value here can become negative if these two conditions exist. But we also realized from the examples of ice with its melting and freezing that even if you had a reaction that was exothermic but taking place with a fall in entropy, or a reaction that was endothermic but associated with an increase in entropy, that both of these conditions, depending on the temperature, can also give rise to a spontaneous reaction. So today, we return to this equation, the Haber process. Today, we focus on Gibbs free energy, spontaneity, and Kc, the equilibrium constant, and how they're all connected. And here we realize that the reaction is exothermic in this direction, meaning that heat energy is released from the system. This heat energy is capable of doing work. So it's something that would contribute towards the creation of a negative value for delta G. But on the other hand, the change in entropy is negative. And when the change in entropy is negative, this does not contribute to the system's ability to do work, and therefore it does not contribute to creating a negative value for delta G. But let's consider what the Gibbs free energy associated with this reaction at 25 degrees Celsius would look like. And here we plug in the enthalpy change for the reaction, negative 91.8 kilojoules. We convert 25 degrees Celsius to a temperature in Kelvin, 298, and then we get the change in entropy associated with the process. And we put that into this equation. Working out this part of the equation comes to 58.7 kilojoules, with the Kelvin cancelling with the Kelvin here, and the negative multiplied by the negative, giving you a positive. Solving here gives you a negative value for delta G, negative 33.1 kilojoules. Once we get a negative value for delta G, then it means that the system is capable of releasing free energy to the surroundings. It's capable of doing work. And when this happens, we say that the reaction is spontaneous. But as this equation suggests for the Haber process, it's a reversible reaction. But is it going to be reversible at 25 degrees Celsius? At 25 degrees Celsius, if everything were reversed, then this sign would become positive, and this sign would become negative. And this final answer would be positive 33.1 kilojoules. A positive value for delta G means we have a non-spontaneous process. But how then is it that we say that this reaction does happen, and the reverse reaction does happen for the Haber process? Well, it doesn't happen at 25 degrees Celsius, but it does happen at the temperatures at which the Haber process happens, which might be around 400 degrees Celsius. Now, if the temperature is 400 degrees Celsius, then it means that this value would have to be increased to well over 600. And if this value is increased to well above 600, and we're looking at the reverse process, then this value here, when you solve for it, would come to more than the positive value for the 91.8 kilojoules. And when you end up solving for delta G at a higher temperature, you would get a negative value for the Gibbs free energy. And what that indicates is that the reverse reaction is spontaneous at higher temperatures than room temperature. Why then do we have the Haber process at high temperatures? And of course, the answer to that question is because the rate of the reaction would be too slow for it to be economical. So now that we realize that there's this reversible process, we can consider this diagram here. And for a reaction where 1 mole of reactants is going to go to 1 mole of products, and the reaction is spontaneous in both directions, like the Haber process at an elevated temperature, we can think of it as the reactants having this amount of energy before it begins to become converted to products. And this amount of energy here in the rubber band can then be released. And as it's being released, the reason that we have a fall is because the system is losing what it has to the surroundings. So there's this negative value. And it loses and loses and loses, becoming products. And then here it has nothing more to lose. At this point, this side has energy that it can release to do work and cause the reverse reaction to happen. So there's this balance between the Gibbs free energy associated with the forward reaction and the reverse reaction. And we know for a reaction like this that is reversible, that we can solve for this value Kc, the equilibrium constant. And you should know from previous lessons how to derive Kc, the equilibrium constant, given this equation. But now, we realize that the Gibbs free energy is related to the equilibrium constant, because at this point of equilibrium, the Gibbs free energy change for a reaction is 0. And this relationship between Gibbs free energy and the equilibrium constant allows for this equation to be derived. And here we see that the Gibbs free energy change, delta G, is equal to negative RT multiplied by the natural log of K, the equilibrium constant, ln K, where R is the gas constant, T is the temperature in Kelvin, and K, the equilibrium constant. Let's move in and look at a couple practice questions to help us master this concept.